So using the previous prime divisor theorem, we can easily prove the so-called special problem, which is just a special case of the theorem we want to prove. And the special problem says that if you have primes P, Q, R and S, such that the product of P, Q is the same as the product R, S, then P and Q must be the same as R and S in some order. Either P is equal to R, in which case Q is S, or P is equal to S, in which case Q is equal to R. Okay, so now for the proof, well, as always, write down what we know, which in this case is that P, Q, R and S are primes, and PQ equals RS. The way to look at this is that we have a number which we can write in the form PQ, where P and Q are primes, and we can also write in the form R and S, where R and S are primes, and we want to show that the primes are the same, perhaps in a different order in each case. Because P divides PQ, then it must divide RS because that's the same number, so we have the P divides RS, and then by the previous prime divisor theorem, this means that either P divides R or P divides S. Now if P divides R, because P is a prime and because R is also a prime, then P must equal R. And if P divides S, then similarly we must have that P is equal to S. So we have the two situations where either P is equal to R, in which case in here we have PQ is equal to PS. We cancel the P's, we divide through by P, and we get the Q is equal to S. So we have that Q is equal to S. And if P is equal to S, then similarly we get that PQ is equal to RP, and so Q is equal to R. And that completes the proof. Before next proving the uniqueness of prime factorizations, we need one very small generalization of the prime divisor theorem. And that is that if P is prime and P divides a product of integers, then P must divide at least one of them. The prime divisor theorem was the case in which we just had two integers. So here is the prime divisor theorem, and the proof is simple. Because P divides A1 times A2 up to AN, by the prime divisor theorem, P divides A1 or P divides A2 times ... up to AN. And similarly, if P divides A2 ... up to AN, then it must divide A2 or divide A3 times ... up to AN, and so on. So in other words, P divides A1 or P divides A2 ... or it divides AN. And of course it could well divide more than one of them. So that's the end of the proof.